Hey guys, welcome back to another video. In this video, I'll be wrapping up Unit 1, which is going to be on limits. So as I'm merely just wrapping up my content for Unit 1, it's going to be a pretty short video as I'm only going to be covering two concepts. The first concept, which I'll be talking about, is our removable / non-removable discontinuities. The second concept I'll be introducing and explaining is the IVT, aka the intermediate value theorem. So with all that being said, let's jump right into the actual video. So let's start with a removable discontinuity. Now let me present to you a graphical representation of what a removable discontinuity can look like. This is just an example. Now I may have already mentioned this, but this is an example of a removable discontinuity in a graph. Now, what makes a discontinuity removable, you might be asking? Well, all that means in simple terms is if you can take this discontinuity right here and do something to it, such as a filling in the hole, and if that makes the graph continuous, then it can be classified as a removable discontinuity, as you just removed that discontinuity. So let's see if we can do that with this example right here. Well, we can fill the hole. Now, if we fill the hole, since there's no discontinuities in the graph anymore, we can say that this is indeed a removable discontinuity, right? Yeah. So now let's look at a function. Let's say f of x is equal to x squared minus 9 all over x squared plus 3. Okay? So the best way to figure out if there's a removable or a non-removable discontinuity in this case is to try factoring some terms out. So the numerator can be factored into x minus 3 and x plus 3. Now, this can't be factored down, so this is just remain x squared plus 3. So, in this case, we can cancel any terms out, so therefore this would be classified as a non-removable discontinuity. Now, what if we have a slightly different but similar example? X squared minus 9 over x plus 3. Now, the numerator still factors the same, as it's the same numerator, of course. Now we have x plus 3 in the denominator, so you may notice that these terms actually do cancel out, and we're just left with f of x is equal to x minus 3. But if you remember from algebra 2, if you have a fraction as a function, and if you could cancel out a term from the numerator and the denominator, that actually classifies at a whole. So if we look at the term that can't cancel it out, x plus 3, a whole occurs when x is equal to negative 3, as the denominator cannot equal 0. So whole at x is equal to negative 3. So because this is a whole, as I already demonstrated and shown you guys in the last example, we could just fill in the hole and then the graph would be classified as, or the discontinuity would be classified as a removable discontinuity. So let's just write it up here. This is non-removable. However, this is removable. Now, the AP exam may, actually not may, it will ask you to classify certain discontinuities as removable or non-removable discontinuities. Now, they might not ask you this directly, but they will ask it as almost a secondary question. So you have to be able to classify discontinuities as removable or non-removable. So this is the same example that I presented to you in the last clip, and we classified this as removable, right? Now I want to show you guys an example of what a non-removable discontinuity might look like. Let's say you have a graph. So let's say that the graph looks something like this. So as you guys may know, this is actually called a piecewise function. And now I think I want to introduce to you a pretty easy way to classify a discontinuity as non-removable. If the limit as x approaches the value where the discontinuity occurs, if that limit exists, then the limit or the discontinuity can be classified as removable. However, if the limit does not exist, then the discontinuity has to be classified as non-removable. Again, if the limit exists, it's a removable discontinuity. If the limit does not exist, it's a non-removable discontinuity. So let's call this A. So the limit as x approaches A of f of x is what? Now, if you recall from my part 2 video of limits, for a limit to exist, the left side limit has to agree with the right side limit. They have to be approaching the same value. And in this case, that's simply not the case. Okay? So we can say that the limit does not exist. Therefore, because a limit does not exist, this is a non-removable discontinuity. Now, let's start talking about the IVT, the intermediate value theorem. So right now you'll see a screenshot of the formal definition of what the IVT is. But now this may look complicated as is, but it's actually quite simple. So let's look at it from a graphical perspective, okay? Let me actually extend the graph. Let's say that you have a continuous function. So f of x is continuous. Okay? Let's call this point A. Let's call this next value B. So all the IVT is stating is that if you have a continuous function and the output value of the first input value, so the output value of A is negative and the output value of B is positive, if the function is continuous, then the IVT states that there must be a 0 at some point between these two bounds, and here it occurs here. But the graph could look like anything. Actually, it could be a squiggle, it could be a parabola. Okay, it doesn't matter, because if the function's continuous and one side is negative, or one output value is negative and the other output value is positive right here, and knowing that the function's continuous, you can just logically say that the graph has to cross the x-axis at some point, right? It's actually extremely logical. Now, why did I talk about this? And why is there even a name for this theorem? Well, on the AP exam, in certain free response questions, you will be asked to justify your answer, and in many cases you'll have to explain why the IVT applies here. Now, you could try to use logic to explain why there's a 0 in a function, but some of the grading policies on the AP Calculus FRQ rubrics, you specifically get a point for mentioning and explaining how the IVT is used in this instance. So if you do want to run the risk of not mentioning the IVT because you didn't bother to memorize it, well, then you risk losing a point. And I just don't recommend that because it's so easy to remember this, and it's so easy to earn the point, considering that all you need to do is talk about how the function is continuous and how the IVT applies in this instance. Alright guys, that's enough calculus for today, and with this video being done, we're officially wrapping up Unit 1, which is about limits. So in the next video, I'll be talking about Unit 2, which is going to be a bit harder, but don't worry. Now, one more thing that I wanted to talk to you guys about is that I'm only skimming over the essential concepts for the AP exam, but in order for you to score a 5 and do really well, you have to spend hours doing practice problems. That way the concept actually gets into your head and you actually start learning. There's no substitute for spending hours on practice problems. That's the only way I got a 5, and that's the only way you can get a 5 as well. But just don't forget to follow the TikTok, subscribe, and drop a like. And I'll see you guys again next video.